Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will discuss about the power series solution about a regular singular point by Provenance method part number 3. In the first part of this topic, we discussed about the power series solution when initial roots are not differ by an integer. And in the part number 2 of this topic, we discussed about the power series solution about regular singular point when initial roots are same. Now, in the third part, we will discuss about the power series solution by Provenance method when the roots are distinct but they are not differ by an integer. Now, we will start our topic with the power series solution about a regular singular point. So here we have a y double dash plus pxy dash plus qxy equal to 0 be a second order homogeneous linear differential equation, and we know that x0 is said to be ordinary point of the differential equation y double dash plus pxy dash plus qxy equal to 0 if the limit x tends to x0 px and limit x tends to x0 qx both should be exist, and a point x0 is called singular point of the differential equation y double dash plus pxy dash plus qxy equal to 0 if the limit x tends to x0 px or limit x tends to x0 qx does not exist, and a singular point x0 is said to be regular singular point of the differential equation y double dash plus pxy dash plus qxy equal to 0 if the limit x minus x0 into px and limit x minus x0 whole square into qx both exist. In this case, we can find the power series solution by Provenance method. And if one of the above limit x tends to x0 x minus x0 px or limit x tends to x0 x minus x0 whole square qx does not exist at x0, then x0 is called irregular singular point. In this case, we can't apply the Provenance series method. Now we will see the types of solution in Provenance series method. Here we know that the types of solutions in Provenance series method depends on its initial root, which can be obtained by putting the minimum value of n during the example calculation. Here we can find the initial root by another method, as we know that limit x tends to x0 x minus x0 px is exist, call it p0, and limit x tends to x0 x minus x0 whole square qx is equal to q0, both are exist. So initial equation also can be obtained like r into r minus 1 plus p0r plus q0 equal to 0, which is also obtained by putting the minimum value of n during the example calculation. By factorizing the initial equation, we get the two roots because our initial equation is quadratic equation. Now if the roots are not differ by an integer, then it is a case number 1 of the Provenance series method. If the roots are real and same, then it is a case number 2. And now the third case of the Provenance series method is initial roots are distinct and not differ by an integer. In this case, we can find the one solution by putting the r equal to r1 or r2 in the recurrence relation, and we get the power series solution as y1 equal to x minus x0 raised to r1 into sigma n equal to 0 to infinity an x minus x0 raised to n. And in this case, we can also take the r2 in place of r1, but we can't find the second solution using the second initial roots because they are linearly independent in case of when r1 and r2 differ by an integer. Here we will find the second solution by taking the partial derivative of y with respect to r and then put the r equal to r1 in that partial derivative. So the general solution of differential equation y double dash plus pxy dash plus qxy equal to 0 about a regular singular point is given by y equal to c1 y1 plus c2 y2, where c1 and c2 are arbitrary constant, and first solution y1 is obtained by directly putting the r equal to r1 or r2, and the second solution is obtained by taking the partial derivative of y with respect to r and then put the r equal to r1 or r2 according to the first solution. Now we will see the one example related to this topic. Here find the power series solution of x into x minus 1 y double dash minus x y dash plus y equal to 0, and we have to find the power series solution about the point x0 equal to 0. Here we divide our equation by x into x minus 1. So px equal to minus 1 upon x minus 1 and qx equal to 1 upon x into x minus 1. So we can say that x0 equal to 0 and 1 both are singular points. But we want to find the power series solution about only singular point x0 equal to 0. So we omit the singular point 1 and we check the is x0 be a regular singular point or not. Here px is minus 1 upon x minus 1 and qx is 1 upon x into x minus 1. Limit x tends to 0, px equal to limit x tends to 0 minus 1 upon x minus 1 is equal to minus 1 upon minus 1, that is 1, which is exist for our point x0, but limit x tends to 0 qx, that is limit x tends to 0 1 upon x into x minus 1 does not exist. Therefore x0 be a singular point of differential equation. Now limit x tends to x0 x minus x0 into px, which is equal to limit x tends to x0, that is 0, and px is minus 1 upon x minus 1, that is equal to 0, which is exist. Now limit x tends to x0 in x minus x0 square into qx, that is equal to limit x tends to 0 x square 1 upon x into x minus 1, that can be written as limit, that is equal to limit x tends to 0 x upon x minus 1, that is equal to 0, which is also exist. Therefore we can say that x0 equal to 0 be a regular singular point of the differential equation. So now x0 equal to 0 be a regular singular point of the differential equation. Now we can find the power series solution by Provenance method for this differential equation. Now our power series solution y equal to sigma n equal to 0 to infinity an x raised to n plus r with a0 not equal to 0. And so y dash equal to sigma n equal to 0 to infinity n plus r an x raised to n plus r minus 1, and y double dash equal to sigma n equal to 0 to infinity n plus r into n plus r minus 1 an x raised to n plus r minus 2. Now in the second step we will put the value of y dash and y double dash in the differential equation. Here we replaced y dash, y double dash in the summation form. Now we multiply each coefficient inside the summation and we finally get these terms. Here in the second summation we have a power of x is x raised to n plus r minus 1, and in other summation we have a power of x is x raised to n plus r. Now we will set the power of x as a x raised to n plus r in each summation, so we have to change in second summation. So we replace n by n plus 1 in the second summation only. Therefore, now we have a power of x in each summation is x raised to n plus r. Here in the second summation, after replacing n by n plus 1, we have a summation n equal to minus 1 to infinity n plus r into n plus r plus 1 an plus 1 x raised to n plus r, and other summations are as it is. Now, by putting the minimum value of n, we can get the initial equation for the differential equation and then find the initial roots. According to that, we can find the further solutions. So, here our minimum value is n equal to minus 1. After putting the n equal to minus 1, we get the minus r into r minus 1 a0 x raised to r minus 1. And after that, we can combine the all summation and we are taking the x raised to n plus r as common, and from this term we can find our recurrence relation in terms of n and r. Now we will find the recurrence relation by comparing the coefficient of x raised to n plus r, and by comparing the coefficient of x raised to r minus 1, we can find the initial roots because our minimum value is n equal to minus 1. After putting n equal to minus 1, we get r into r minus 1 a0 equal to 0. As we know that a0 is not equal to 0, so our initial equations is r into r minus 1 equal to 0, and therefore r1 equal to 0 and r2 equal to 1 are initial roots for the differential equation. Here we can see that r1 minus r2 is minus 1. That means initial roots are differ by an integer. Also they are distinct. So it is a case number 3 of the Frobenius series method as we discussed. Now by comparing the coefficient of x raised to n plus r, we get the for n greater than or equal to 0, n plus r plus 1 into n plus r an plus 1 equal to n plus r minus 1 whole square into n, and this is valid for n greater than or equal to 0, and by taking the subject as n plus 1, we get the recurrence relation an plus 1 equal to n plus r minus 1 whole square upon n plus r plus 1 into n plus r an. This recurrence relation is depends on value of r and it is valid for n greater than or equal to 0. Here we have a two different value of r, r1 r equal to 0 and r equal to 1. According to the r equal to 0, we have a recurrence relation an plus 1 equal to n minus 1 whole square an in upon n into n plus 1, and it is also valid for n greater than or equal to 0. For r equal to r1, we have a recurrence relation an plus 1 equal to n square an upon n plus 2 into n plus 1. It is also valid for n greater than or equal to 0. Here for r equal to r1 equal to 0, some coefficient of the power series solution becomes infinite. So we replace a0 by b0 into, and then after calculating properly, a1 equal to r minus 1 whole square b0 upon r plus 1. a2 equal to r square into r minus 1 square upon r plus 1 whole square into r plus 2 b0, and a3 equal to r square r minus 1 whole square upon r plus 2 whole square into r plus 3 b0. Now we will find the first solution for r equal to r1 equal to 0. Here y1 equal to x raised to r1 into a0 plus a1x plus a2x square plus a3x cube be a power series solution for initial roots r equal to r1 equal to 0. After putting the value of a1, a2, a3 in the power series, and also we replaced a0 by b0r, and then we get the power series in terms of x and r. After putting r equal to r1 equal to 0 in this series, we get the second term is 1 and other terms are 0. So finally our solution is y1 equal to b0x for r equal to r1 equal to 0. Now to find the second solution, we are taking the partial derivative of y with respect to r and then put the r equal to r1 equal to 0. Here we differentiate the power series, and finally after putting the r1 equal to r equal to 0, we get the most of the terms of series are 0 and the non-zero terms are given in the red color. After simplifying properly, we get the second solution, which is y2 equal to b0 into x log x plus 1 minus 3x, and we already obtained the y1 equal to b0x. So finally we have a general y1 equal to b0 x and y2 equal to x log x plus 1 minus 3x. So our general solution of the differential equation, x into x minus 1 y double dash minus xy dash plus y equal to 0 is c1y1 plus c2y2, where y1 is b0x and y2 is b0 into x log x plus 1 minus 3x. Here c1 and c2 are arbitrary constant. So here we discussed the third case of the Provenance series method. Already we discussed the first case and second case of the Provenance series method in the previous lectures. Thank you very much.